In part 1 of drawing orbital diagrams and Bohr models, we learned how to draw orbital diagrams and Bohr models for elements up to calcium. And then in part 2, we focused on the D block and how to draw orbital diagrams and Bohr models for elements up to barium, where we're incorporating the D block and expanding on the limits of the number of electrons that can fit in each orbital. Today, in part 3, and the final part, we are going to learn how to draw orbital diagrams for charged particles, which we know are called ions. So we will start with a more simple example of an element right here, fluorine, not too far down on the periodic table. And I have here on the left, I have the Bohr model and the orbital diagrams for fluorine 20. So we already know how to calculate the number of protons, neutrons, and electrons. It is uncharged, so the number of electrons equals the number of protons. And we have protons and neutrons drawn in the nucleus, and then the electrons in the correct shells around the nucleus. For fluorine 20, we have 2 electrons in the first shell because that is the most that that first shell can hold. And then we have 7 in the second shell because if we look on the second energy level, there are 1, 2, 3, 4, 5, 6, 7 electrons for fluorine. So we'll just count left to right. So that is why I have 7 arrows drawn on my orbital diagram, because the arrows represent electrons, and I filled in my orbitals. My 1s got filled in, and then my 2s got filled in, and then I filled in 2p until I got to fluorine. So 1s filled in, 2s filled in, and the 2p was filled in up until we got to fluorine, and that's why it's not completely full. All right, but today we're going to learn about how things are different when we have a charge. And you might be able to just pause the video and think about what a charge means for the number of electrons. And so first of all, we'll discuss what changes when we have a charge. We already talked about this when we introduced the concept of ions before, but we remember that this proton number, this 9, is unique to fluorine, and it is never ever going to change. And I always say you might as well write the proton number in pen because it does not change. So fluorine has 9 protons. The neutron number is not going to change for if there's a charge either, because it wouldn't make sense to change the number of uncharged particles when everything's the same except for the charge. Since the uncharged particles, the neutrons, do not affect charge, they're not going to change. And then we notice that we have a -1 charge here. So let's highlight that. We have a -1 charge here. That tells us that there are more negative charges than positive charges. Specifically, how many more? Well, we'll look at this number 1 right here. That tells us that there is 1 more negative charge than positive charge. And if we translate that into terms of protons and electrons, that means we have 1 more electron than we have protons. So the electron number is now just going to be 1 number greater than the number of protons. So the number of protons is 9. That means the number of electrons is 1 number greater than that. So we have 10 electrons for a fluorine with a -1 charge. So I can fill in my Bohr model, and again, we have 9 protons. That will never change for fluorine. We have 11 neutrons because the neutron number is not impacted by a charge. And then we can fill in our electrons. The first shell holds up to 2 electrons. And then the second shell, it can hold up to 8. And if we look at our number here, we already have 2 drawn, so we need to draw in 8 more to get to 10. So we're going to put 8 electrons in this second shell. Now I can fill in my orbital diagram, and we are going to really, what I like to do is I like to look at the periodic table and find where an element with that number of electrons is located. So again, we are doing fluorine. However, I erased it because I didn't want to cover up a number. However, I like to just look and find on the periodic table an element that has this number of electrons, because the atomic number on the periodic table represents the number of protons, but it also represents the number of electrons when the atom is uncharged. But since fluorine has a -1 charge, it's going to have the same number of electrons as neon would as an uncharged neon atom. So we can still, so if by doing that, we can check mark our way through the periodic table as we would for a normal orbital diagram, but now for this charged orbital diagram for this charged ion. So let's check off where we're at. We're first going to check off hydrogen and helium and draw in our arrows for those 2 elements. Next, we're going to keep moving left to right. So we are now at lithium and beryllium, and we're going to check off our periodic table there and fill in those electrons. We're going to keep going left to right, and we are now at boron, and then going to keep checking those off. 1, 2, 3, 4, 5, 6. And we got all the way to the element that has 10 electrons, because we have 10 electrons for a charged fluorine with a -1 charge. So if you notice, all I did was, since we have 1 more electron, specifically 1 more electron for fluorine, all I did for the orbital diagram was I just simply added 1 electron. That's the only difference. I wanted to draw it separately so that we could see the difference, but all it is just, if I notice there's a negative charge, I'm just going to take it for a negative charge. I'm just going to draw that many more arrows. So for -1 charge, I just draw in 1 more arrow. Now we will deal with, and then for the Bohr model, I just draw in 1 more electron. And I have to figure out where that electron goes, which could be tricky, but for here, we can fit up to 8 in that valence shell. And so I'm just going to put in 1 more electron, and it'll work out for that one. Now let's look at when we have a positive charge. So fluorine with a +1 charge will, you can probably pause the video and guess what's going to happen. But a +1 charge instead of a -1 charge, let's look at how that affects our subatomic particles. Again, the number of protons is not going to change. We have 9 protons, and the number of neutrons would not make sense to change either, since the only difference here is that it has a charge. The number of electrons, we can calculate that, and looking at our charge, we have 1 more positive charge than negative charges. That means we have 1 more proton than we have electrons. So if we have 9 protons, that means 9 is 1 more than what number? 9 is 1 more than 8. So we have 8 total electrons. I can fill in my Bohr model with my protons. So we have 9 protons. We have 11 neutrons. Then I can start filling in my electrons. I have 2 electrons in the first shell, because the first shell holds up to 2, and we have more than 2 total electrons here. And then I need how many more electrons to get to 8? Well, I already have 2 filled in, so I need 6 more to get to 8. So we have 6 electrons on the outer shell, on that valence shell. So before, if we're comparing to this over here, this model for the uncharged fluorine, remember before when there was a -1 charge, all we did was we added 1 electron? Well, now all I'm going to do is take 1 electron away. But be careful. Let me zoom in. Be careful. The electron that we're going to take away, we would not take away this electron. Don't take away that one, because remember, these electrons, they like to socially distance, and we need 1 electron per box before any boxes get 2 electrons. So therefore, I would need to take away this electron, not this one. So let's draw that out on our other model with our new color scheme. I've got an electron will go here and here. And if we want to check off where we're at on the periodic table, just like we did before with this negatively charged example, let's find the atom that has 8 electrons. Let's find something else on the periodic table that has 8 electrons. That would be oxygen here. So we can check off as we go through the periodic table and then just stop at the element that has 8 electrons. So let's look at helium. So let's check off, we already filled in the 1s orbital, so let's check off the 1s orbital, first energy level s orbital. Next, we can look at the 2s orbital. We can fill in our 2 electrons and check off where we're at on the periodic table. Check off here and here. Next, we'll keep going until we get to oxygen. So we're going to check off here, here, 3, and 4, and we're now at oxygen. So we are going to have a total of 1, 2, 3, 4 electrons drawn in to the 2p orbital. Again, make sure you don't, if you just want to draw it, another way to accomplish this is to just draw for fluorine that's uncharged and then add or subtract the number of electrons you need to. But if you do it that way, I just want you to be careful not to erase the wrong electrons or the wrong arrows. You need to make sure that the boxes that each box has in the p orbital, each box has 1 electron before any of them have 2. So don't erase the wrong arrow there. So these are the correct answers for fluorine with a uncharged, -1 charge, and a +1 charge. Let's do a little bit more, slightly more difficult example in carbon-13 with a -6 charge and a +5 charge. So here on the far left, I have carbon-13 drawn and the correct Bohr model and orbital diagram already filled in. Let's look at what happens when we have carbon-13 with a -6 charge. And it might be a good time to pause the video and attempt this on your own if you want to, if you think you understand what's going on. This is a little bit different, but I think that some of us will be able to solve this from what we already know at this point. So I'll start filling this in and solving where we're at. So carbon-13 with a -6 charge is going to have 6 more electrons than we have protons. That means we will have 12 total electrons. So again, this -6 means we have 6 more negative charges than positive charges. So if we have 6 positive charges, what's 6 more than 6? It's 12. So 12 total electrons. So let's look at how we're going to fill that in on the periodic table, or on this Bohr model. So I can fit 2 electrons in that first shell. we said that we can fit up to 8 electrons in the second shell. Well, 2 plus 8, that equals 10. So we're not at 12 yet, we need to get to 12. So that means that I'm going to have to add another energy level here so that we have room for 2 more electrons. Because we can never fit more than 8 electrons in the valence shell, and we especially can't fit more than 8 in the second shell, because remember that equation 2n squared? That's the maximum number of electrons that can fit in each shell, where n equals the shell number or energy level. So we have 2 electrons in the first shell, 8 electrons in the second shell, and so we have 10 total electrons drawn. I need to draw 2 more electrons in order to get to 12. So I will draw 2 electrons in the final shell, and that will get me a total of 12 electrons drawn for this ion, which is the correct number that we calculated there should be. I can now fill in my orbital diagram with the correct number of electrons. So there should be 12 total electrons, and what I would recommend doing is find the element that has 12 electrons, so that would be magnesium here, and then just fill in the orbital diagram as if we were doing magnesium, because the orbital diagram for magnesium is identical to the orbital diagram for carbon with a -6 charge. Remember, the orbital diagram only tells us the number of electrons. So we can fill in as if we had magnesium. So I'm going to check off where we're at on the periodic table. We can check off box here, and that fills in the 1s orbital. Next, we're going to keep moving left to right, so we have lithium and beryllium. We can check off those 2 electrons and draw them in on our model. We can keep moving left to right, and we can check off where we're at. We're going to keep going. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, wait a second. Did we just run out of orbitals and boxes that we can put these electrons in? Well, let's think back to what we did for the Bohr model example. We had to draw an extra energy level. So we're going to have to do the same thing here, where we're going to have to draw an extra energy level, or however many boxes we need to fill in the rest of the electrons. We have 10 total electrons drawn, and we need to add 2 more. Specifically, we need to add 2 more that are in the 3s orbital. So that means I'm just going to draw another box and label it 3s, and I will fill in my electrons there, because we just moved left to right on the periodic table, and we are now in the 3s orbital, and we stop when we get to magnesium here. So we're going to fill in these 2 electrons, and then voila, we are now done with our orbital diagram for carbon with a -6 charge. We have 12 total electrons drawn in, and we calculated that there should be 12 total electrons. You can also do the highlighting method, where we said we have two total electrons in the first energy level, 2 electrons in the first energy level, and then 8 electrons in the second energy level, 8 electrons in the second energy level, and 2 electrons in the final energy level, 2 electrons in the final energy level. Feel free to do that. I would definitely recommend, but I don't want to take the time to do that on every single example. All right, next we have carbon with a +5 charge. So if you want to take a guess on how to do this, pause the video real quick and try to figure it out on your own first. All right, carbon with a +5 charge. Again, the protons and neutron number is not going to change. And let's calculate how many electrons there should be. So if we have 6 protons and we have a positive 5 charge, that means we will have 5 more positive charges than negative charges. So if we have 6 total positive charges, 6 is 5 more than what number? 6 is going to be 5 more than 1. So this means that we have 1 total electron for carbon with a positive 5 charge. So I'm going to draw in the electrons on the Bohr model here. And since I only have 1 electron, it's going to go in the first energy level by itself. You are welcome to keep the second energy level drawn in, because it doesn't matter. These energy levels exist whether we have electrons in them or not. These energy levels exist. So you can keep them. You can keep as many energy levels drawn as you want, as long as you only fill in the relevant ones with the electrons. But for simplicity's sake, I like to just make it look more clean and have the shells only present if there are electrons located in them. So I'm just going to erase this second shell and only have that first shell drawn. Next, when I fill in my orbital diagram, I have 1 total electron in this ion. So I'm going to draw. I can look on the periodic table and see what element has 1 total electron. We have hydrogen has 1 total electron. So I'm just going to draw 1 arrow and check off where as we go. Boom, we're already where we're at, where we need to go. So there's 1 total electron, so I'm just going to draw 1 total arrow in the 1s orbital, because on my periodic table, hydrogen is in the 1s orbital. All right, just like before, you have the option to draw the extra energy levels. You also have the option to keep these extra energy levels drawn in. It is not wrong to have the 2s and 2p energy levels and orbitals drawn in and not filled in. You can leave it like this. But for simplicity's sake, I like to make it look a little more clean and have them erased unless they are actually filled with electrons. So this would be the correct way to draw carbon with a positive 5 charge. There's just 1 electron by itself in the 1s orbital. Lastly, I'm going to do one more, a little bit more complicated example. This is utilizing the D block. So we're going to do gallium here, which is located right here on the periodic table. First, we have gallium drawn with no charge, and where we have 31 protons, and since it's uncharged, also 31 electrons. So this is how gallium is supposed to be drawn with the Bohr model and the orbital diagram. We have 31 total electrons filled in on the Bohr model, and we also have 31 arrows representing the 31 electrons for gallium on the orbital diagram. Now let's try gallium with a -4 charge. So we have, and again, I recommended last time that if we have an element that is somewhere after calcium, it's going to be easier to draw in the orbital diagram first. So I'm going to go ahead and do the orbital diagram first. So gallium with a -4 charge, all you're going to end up doing, like I said before, is you just fill in 4 more electrons. So 1, 2, 3, 4. That's what it's going to look like, except I'm going to redraw it all over here on the right. So one way to do it is well, let's first calculate how many total electrons. If we have 31 protons and we have a -4 charge, that means we have 4 more electrons than protons. So what is 4 more than 31? It is 35. So 35 total electrons. So you can find the element on the periodic table that has 35 electrons and then draw in the orbital diagram as if you had that element. So check off as we go. We're going to fill in the 1s. Next, we will fill in the 2s. We're going to keep moving left to right. We are now at the 2p. Fill those in. Keep moving left to right. We are now at 3s. Fill those in. Keep moving left to right. We are now at 3p. Fill those in. Keep moving. So 3p, we filled those in. We now need to move to 4s. And I didn't show the shift in the 3D orbital, but yes, the 3D orbital is located like up here, and then it shifts down, but that's not like the most important concepts. Just know that the 4s, you're always filling in the order of left to right on the periodic table. So the 4s is going to get filled in before the 3D. So 4s, we're going to fill that in on the periodic table, and then fill in our arrows here. And then keep moving left to right. So we are now going to fill in the 3D. Don't forget that the d orbital, even though it's located on the 4th row of the periodic table, it's the 3rd energy level. So let's see how many we need to fill in there. Keep checking off boxes until we get to the element that we said we're going to, bromine. So we're going to fill in that d orbital all the way. All right, we are still not at the element that has 35 protons or 35 electrons. So we're going to keep going. 1, 2, 3, 4, 5. Again, we don't stop at gallium. We're stopping at the element that has 35 electrons. So an uncharged bromine has 35 electrons. Therefore, and since the gallium with a -4 charge has 35 electrons, that's where we're going to stop. So we just said we were going to fill in 5 electrons in the 4p orbital. So I'm going to draw in those 5 electrons. 1, 2, 3, 4, 5. Looks like our orbital diagram is complete. Next, we have we can start filling in the Bohr model. I'm going to use my highlighters this time because it is a little bit more easy to see when I have these highlighted. So the first energy level, everything designated with a 1, is going to correspond to this first energy level here. And I have 2 electrons on that first energy level. The second energy level has 1, 2, 3, 4, 5, 6, 7, 8 total electrons drawn in because we have 8 arrows. So on this second energy level, we have 8 electrons. On the third energy level, I'm going to count how many arrows I have drawn in. And the third energy level, everything with a 3 in front of the letter, so 3s, 3p, and 3d, if we combine all those, we have a total of 18 electrons for the third energy level. So when I highlight the Bohr model, the third energy level, we have 18 electrons. Now this final energy level here, we will do blue. Did not mean to do that. So this final energy level, we have 1, 2, 3, 4, 5, 6, 7 total electrons drawn. So that's going to correspond to 7 electrons going in the valence shell. So here we're going to have 7. We are going to have 7 electrons in the valence shell. So that is gallium with a -4 charge. This next one, this should be probably the hardest example, where we have gallium. Oh, also, I wanted to point out, we said that gallium with a -4 charge should look pretty similar to bromine here. If you recall, in one of the other videos, we covered bromine. So let's scroll up and look at what the orbital diagram looks like for bromine. So again, we have everything filled in up to the 4p, and we have 5 electrons in the 4p orbital. So let's scroll up to our example of bromine real quick. And then, wow, it looks very similar. In fact, it looks the exact same. So the orbital diagram for bromine is the exact same as the orbital diagram for gallium with a -4 charge. So keep that in mind. That'll be a valuable way to double check your work. All right, we're going to do our final example here, where we're going to have gallium with a +3 charge. So again, I have, for an easy comparison, I have an uncharged gallium, the Bohr model, and orbital diagrams drawn on the left here. A +3 charge is going to mean that we have 3 more protons than electrons. So we said that we have 31 protons, and that number is not going to change. If we have 3 more protons than electrons, that means if there are 31 protons, well, 31 is 3 more than what number? 31 is 3 more than 28. So we have 28 total electrons for gallium with a +3 charge. So a couple ways you could do this. You could zoom in on this orbital diagram for gallium that is uncharged and then erase 3 electrons. But you have to make sure that you erase the correct 3 electrons. And that's where I think a lot of us are going to make a mistake. So I'm going to show it the long way, and to explain why we're erasing the electrons that we do. So 28 electrons. So I like to recommend to look on the periodic table and find the element that has 28 electrons. And right here. And that might give us a hint on why we have to erase certain particular electrons from the orbital diagram. So we'll start drawing in our arrows to represent until we get to this element here that has 28 electrons. So we can check off as we go on the periodic table. We're going to fill in those 2 in the 1s orbital. Keep moving left to right. We're going to fill in those 2. Left to right, fill in those 6. All right, keep going left to right. Fill in these two, 3s orbital. Keep moving left to right. Fill in the 3p orbital. All right, keep moving left to right. We are now at the 4s orbital. Keep moving left to right. We are now at the 3d orbital. And we're going to fill in 1, 2, 3, 4, 5, 6, 7, 8. So we will fill in 1, 2, 3, 4, 5, 6, 7, 8. So if that is if you did it the erasing way and you erased the correct arrows, then phenomenal job. But I think I have a feeling that a lot of us, if we erase the arrows, we erased these 3, which would not be correct. And I will show you why here when I draw the Bohr model. So the Bohr model, we are going to, let's pull out our highlighter again and start highlighting away. On the first energy level, it's going to correspond to this right here, and we have 2 electrons there. So this first energy level will have 2 electrons. The second energy level, everything labeled with a 2, we are going to have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 arrows drawn in, which is going to correspond to 8 electrons. So 8 electrons there. Next, the third energy level, we are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. So I'll highlight that on my orbital diagram. And those 16 arrows are going to correspond to 16 electrons on my Bohr model. So the third energy level has 16 electrons because we had 16 arrows drawn on the orbital diagram. And then lastly, on the outermost shell, I am going to have looks like we have wrong marker. Looks like we have a total of 2 electrons drawn in. And again, if you want to keep this p orbital drawn in, you are not wrong for keeping that in. Like, you are welcome to keep that in. However, since it is not occupied with any electrons, you do not have to draw it. And to make things look a little more clean, I'm going to erase it just because it's not being used. So you're welcome to keep it. Does not matter. I just happen to erase it because I want to make things look a little more clean. So we have 2 electrons drawn in this 4th energy level, which is going to correspond to 2 electrons drawn on the 4th energy level of the Bohr model. All right, you might ask, Mr. Oxler, why don't I just erase these 3 electrons? Why did I erase some random electrons in the d orbital? Why did I erase the p orbital ones and then a couple from the d orbital? That doesn't make sense to me. Well, let me explain why. So if we scroll back up through our notes, we've done a lot in this unit. So nice work if you've been following along. But we scroll up to, boom, this slide right here. the maximum number of electrons in each energy level is equal to 2n squared. If we were to erase those other electrons, we didn't mess up that rule. However, we made a very important point that we cannot have more than 8 electrons in the valence shell. So the valence shell cannot have more than 8 electrons. Let's look back at the problem that we were on. All right, if I were to have erased these 3 electrons, that means I would have erased this entire valence shell here. If I would have erased these 3 electrons, and then if we look at our orbital diagram, we now have 18 electrons in the valence shell, which is not possible. So therefore, we need to make sure that we erase the correct electrons. We need to make sure that we erase the correct electrons so that we do not end up with more than 8 electrons in the valence shell. So therefore, that's why I recommended finding the element, in this example, finding the element that has 28 electrons. Circle it on the periodic table, and then just do the orbital diagram as if we had that element. Then the orbital diagram will help you figure out how to draw the Bohr model. So that's all I have for us for charged orbital diagrams and charged Bohr models. Real quick though, I do want to talk about the electron configurations. Just keep in mind that the electron configurations are going to be the same for when you find the, let me clarify, when you find the electron configuration of these charged ions, you need to base it on the number of electrons there are. So the electron configuration just tells us the number of electrons there are. It's a way of notation for the number of electrons there are. So if we remember our example here, where we had gallium with a -4 charge, we recognized that what we drew here is identical to what we have drawn for bromine. So the electron configuration for gallium with a -4 charge is going to be the same as the electron configuration for bromine. So let's do a couple of electron configurations before we finish this video of some of the examples we have. So fluorine, so I'll just do these in black, it doesn't matter. So fluorine uncharged, the electron configuration is going to be, I'll do it in purple, I changed my mind. It's going to be 1s2, 2s2, 2p6. And we can follow along where we're at on the periodic table to get that, or we can use this orbital diagram. Especially before we get to the D block, it's going to be fine to just use the orbital diagram. But if we have fluorine with a -1 charge, the orbital diagram is now different. The orbital diagram is actually going to be the same as the elements that has 10 electrons. So we said we calculated 10 electrons when fluorine has a -1 charge. So the orbital diagram is actually going to be the same as an orbital diagram for neon. So the orbital diagram is going to be, and I made a mistake. Let me go back to my previous example. There are 5 electrons drawn in here, not 6. So this is 2p5. But when we add that extra electron, we're going to get the orbital diagram 1s2, 2s2, 2p6. But what if we take away an electron? What if we have a +1 charge? Well, our orbital diagram is going to be 1s2, 2s2, 2p, 1, 2, 3, 4. All right, carbon. We have 1s2, 2s2, 2p, 1, 2, 1, 2. Carbon with a -6 charge. We have 1s2 because there are 2 electrons inside of here, inside of the 1s. Then we have 2s2, 2p6, there's 6 electrons inside of here. And then we have 3s2. This one's pretty easy on the far right. We have carbon with a +5 charge. There's only 1 electron. So we're going to write 1s, because we're in the 1s orbital, and we have 1 electron there. So we're going to write 1s, 1. All right, gallium, this is where it'll get a little bit more tricky. So we'll check off where we're at on the periodic table and write in our electron configurations. So we have gallium. We'll just do the electron configuration for gallium by itself. So we have 1s2. We can check off here, check off here. 2s2, check off here, check off here. 2p6, because we checked off all 6 of these. 3s2, check off here, check off here. Keep moving left to right. 3s2, we now are at 3p, and there are 6 electrons we're going to check off, because we can check all these off and we're not at gallium yet. Keep going. 4s2, we're going left to right. Since the 4s comes before the 3d in the periodic table, we're going to write the 4s first. Then we are now at the d orbital, so we can fill in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we are still not at gallium. So that means we can fill in all 10 electrons on the d orbital, 3d10. Then here, now we are at gallium, so we are going to write, we are on the 4th energy level in the p orbital, so we're going to write 4p, and we just filled in 1 electron. All right, now gallium with a -4 charge. We're just going to have, instead of, it's going to be the exact same thing, but instead of 1 electron in that valence shell, we are going to have 5 electrons in the valence shell. Sorry, I used the wrong terms. Instead of having 1 electron in the p orbital, we now have 5 electrons in the p orbital. So I can write all of this out again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, but again, we have 5 electrons drawn in the p orbital, not 1. So I'm going to write 4p, 5. All right, in our final example, I already have the electron configuration for gallium with no charge. I'm just going to copy and paste this actually. Oh man. All right, that should work. All right, so we have the electron configuration for gallium with no charge. So now what do we think we need to do for gallium with a positive 3 charge? You can pause the video real quick, and then this is the last problem we're solving. But all we're going to do is find the element that has 28 valence, or 20, not valence, but 28 total electrons. That's this element right here, and it's going to be the same electron configuration as that element would have. So we are going to end up removing, again, we removed 3 electrons, and we're going to just change these numbers to where instead of, in the d orbital, instead of having 10 electrons, we calculated that we only have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the d orbital. So we're just going to change this number to 8, and we're going to get rid of the p orbital because we don't have it anymore here. And then this s orbital, well, actually that one's not going to change, but that's going to, so I will write this out for us. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. 8. All right, next class I will show you how to do a shortcut method for these electron configurations. It's less of a shortcut and more of just a simplified way of writing them. But that's all we have for you for charged ions, so orbital diagrams and Bohr models for ions. Next class, we will have a quiz over drawing Bohr models, drawing orbital diagrams, and writing electron configurations for charged particles, or so for ions. And specifically on the quiz, I'm going to be making up ions because I don't want us to just Google on how to draw an orbital diagram and Bohr model for this element, because you're just going to be able to find that on Google. But what you're not going to be able to find on Google is Bohr models and electron configurations and orbital diagrams for charged particles. So that's how the quiz is going to be, so make sure you understand this material. Let me know if you have any questions. Hopefully this all made sense, but we'll keep working through it.